Another draft physics video presentation. Some kind of our first time ever explained video on the single slit. Something nobody ever deals with, and I think I've found the sensible explanation. And you sort of have to say wave theory doesn't account for it because they don't account for it. So the fact that I am accounting for it demonstrates that this is something you understand when you understand that it is clumps, not waves. Anyway, so in this single slit pattern, you'll get variants of a pattern where these little bits here end up the same size, and this thing in the middle can look anywhere from, as I've noticed, 2 to 3 times the size of these bits. And that's always bothered me, that when you look at it, it looks like 3 sometimes, but then when you calculate it out, it's like, no, it's only 2. You can't really make it work. It comes out to a weird number, but you can't just say, well, these bars should be this big and this bar should be this big. Not counting the light. You sit there, because the dark spots are always smaller. And so you try to figure out a node size, a standard size. The offs are as big as the ons, so to speak. And when you try to put them in here, you end up with remainders, and it just doesn't fit. 2 doesn't fit, 3 doesn't fit, and there's a reason. And so that's what I have deduced, observed, figure out, or whatever you want to say. So let's make a single slit here. And so it should be understandable. This is, smaller than a millimeter, something less than a millimeter. A little tiny slit, really. And the idea is that we're counting vectors from 2 point sources. That's what's in the math. And so, they pretend it's waves, but the waves to be in the mathematically correct location have to be here. Which doesn't make any sense, because why would the wave split in the middle? Why would it go through the material? That's not going to happen. So anyway, so it doesn't really work mathematically as a wave, and this scatter idea does actually work and create the right vectors and all of that stuff. So this is what I propose is the true answer, that all you're doing is scattering bits of photon, and you're just reconstructing them, either back in phase or not. No photons are technically destroyed, so to speak. They're just broken, and you put the pieces back together, where this one makes a contribution or piece, and this one sends another piece. This one might send the other piece, and you end up reconstructing the phase of a photon. And in the other places, they're still getting hit by those little bits, but the little bits don't have the right phase. They're in wrong sequence, and therefore it won't be seen as a photon. So the trick is that the vector really starts here and here for these 2 point sources. That's their shortest line, okay? And the whole thing can be understood on an arc. That this line would be, this R would be the same as this R. And what you're really doing is you're going to take what's in here, and you're pretty much going to just project it onto this bigger line. So you're really just saying R, times 1/2 pi. And that basically will do your conversion for you. It'll take this line and tell you something on this scale ends up being projected onto this scale. A difference in the line length. Okay, so this part you don't need because I already pointed it out. So there's a standard number of these little places. There's only a certain number of them. So all you're really doing is taking this distance, we'll call it D. Whoops, I'm probably out of range. Distance. Where's my upper limit mark? I took it away. Oh, that is the upper limit. All right, I'll just do it in here. You're taking the distance here, and you're just dividing it by the wavelength of whatever the light is, and you get a number. Now, the trick is, that no one talks about, is whether you get a whole number or not, right? If I get a number like, say, 17, or I get a number like 17.5, those two numbers mean a great deal of difference to this point and this point. So what's really happening is when they do the center vector, these are really cheat vectors, because these lines aren't going to be shorter or longer. I mean, they're not going to be the same length as this line, right? I mean, if I take this shortest line, this is the true R line, and I move it this way, it's obviously going to be a longer line than this line, the R line. So it's cheating in a sense. It's a place that you really can't go, because this is the shortest line, and you can't make a shorter line without cheating, or a longer, just can't. It's got to stay this one's got to stay the same length, and you're always adding this to it. That's the length difference of the lines. So this is sort of an illusionary center, and so basically as you do this turning, you're creating a fake node. It's not a real node. It's a tiny node. It's only a millimeter wide. No matter what size I project it on, no matter how far the R goes, I still have the same 1 millimeter that this fake node will be created in. So it's a little fake one in the middle. Doesn't mean anything. It's just it's a placeholder. So there's a little bit of light that goes to that spot, and yes, it makes a node, but it's a tiny one. It's only a millimeter wide. It's a tiny millimeter node. Where the other nodes could be an inch. They could be rather large. So it's just a little tiny dot on the target. You won't even barely see it. It's so small. And then it's going to be also disguised, because we know some of the photons just go straight through, and they just end up here diverging, the photon beam. So you end up with a blob of the photon beam. So in the middle you have two sources. You have the photons not interfering, not hitting the surface, not being broken, and you have the original beam, and you have these ones that are going the opposite direction. So the weird thing is here is when you take a regular vector, if you were to draw the vectors that are constructive, that are reconstruction of a photon, you understand that the vectors are both pointing in the same direction, where in this case the vectors are pointing in opposite directions. So it's breaking the rule. See, if I took a vector from here and a vector from here, they're pointing in the same direction. So this one's the abnormal one. This is the aberrant one. And so it really doesn't count for anything. So where you're really starting, this is your 0 point here, and this is your 0 point here. There's 2 0 points for each point source. And that's where the pattern starts. Now if I have 17, if I get even, if it goes in with no remainder, none at all, no remainder, goes in, the wavelength goes perfectly evenly into the distance, well then I know there's an even number of wavelengths, a whole number of wavelengths in the distance, and that this will be now a true node, beginning. We're going to be constructively adding, and so you know that that's where you're going to end up with a full on. And if I had 17.5, that would be a full off. So that difference, a little bit of a difference. So if it was 17.5, if I had a remainder, right, then I would know that that's this line to this line is going to be a destructive. It's going to be a half wavelength off, and so it's going to be a dark. And the light, so the dark will be a certain size, and then the light starts. So the node doesn't start until it's gotten rid of that dark. And so when it's an even number, then it's going to be starting here, let's say. And so the point would be is that you're automatically going to have two nodes that are the distance between the slits apart. So the beginning, the first node, the middle maxima is going to be larger because it's really two maximas when it's an even number. When an even number of wavelengths go into the distance, you'll get two on nodes. So now I want to say a millimeter apart, but I'm trying to think now. If it's an even number, they have to be a little bit overlapped. because we're talking about the center of the light, right? So so this would be the center of one. So the two ons would be overlapping, but they can't overlap more than half, so they're still going to look bigger than a single node. So that's the smallest it can look. And the largest it can look is at the 0.5. So if I give a full half wavelength of extra distance here, then I know that it's a full dark here and a full dark here. And so then the on node won't start till here, and the other on node won't start till here. And then again the laser beam is filling in this middle part, and so this might even look 3.2 nodes worth. It's so big. It might even look like 3 nodes. So it can go anywhere from a little less than 2 to a little more than 3. So the center maxima in its size just depends on what this is, whether it's an even number, go in, a whole number, or not. And if you have this remainder, that's telling you how much dark there is before you get to a bright node. It's telling you how far you are from the center of a bright, which is the tricky part. Yeah. But anyway, the point is just by knowing how many nodes are in here, you can calculate how many would be on this line. And by simply doing this, you know, r, the length of the line, times 1/2 of pi, that'll tell you how many nodes you're putting on. It'll tell you the length of this line, and this line will have the same number of wavelengths in it that this did, and therefore you'll know exactly how big to make these things. But the point is you have to start them. If it's a half wavelength, then you're going to have a half wavelength here at this end, and you're going to have a half wavelength here at this end. In terms of, you're going to have, this will be where there's destructive, the middle of the dark line would be here, and the middle of the dark line would be here. And then you have to calculate where the bright would start from there. And that's where the rest of them will fill in. But anyway, that's why there's a big blob in the center, is because the game really doesn't start except from these 0 points. And these 0 points, the bright bar can be some distance from that point source, if that's not an even number of wavelengths. And only on the special circumstance, the rare circumstance, right? It's much more likely there's going to be this remainder. That'll happen 99% of the time, and only 1% of the time do you get to put an even number in. So most of the time doing the experiment, you're not going to be able to, even if you have a variable slit, most of the time you're going to have a remainder. Most of the time. And it's going to be a rare occasion where you get exactly the right distance. That's exactly a whole wavelength with no remainder. And so that's why you don't see the narrowest center maxima, which would be a little less than 2. But regardless, it explains why the central maxima is completely different looking than the other nodes in the pattern. And I guess that's about all I wanted to say. As I, like every other person thinking about it, have in the past struggled to come up with a really good explanation for why that thing was there. Because the divergence of the beam isn't enough. The laser beam diverges. The light that goes through the center diverges, but it doesn't diverge enough to account for that, the size of that central maxima. But it does diverge enough to make 2 separated nodes look like they're connected as one node. And they're not. They're really 2 separate nodes happening at least, 1 millimeter apart from each other. Alright, so that's, so that's enough. I think I've completed my job here. Yeah, that's all I wanted to do. So just more evidence of why I'm right and they're wrong. And they're profoundly wrong. I mean, they never even thought about it, frankly. They've never even thought about the experiment, really thought about what would happen and how it would happen. I mean, they didn't even notice that their wave centers are in the wrong place. I mean, it's just so bad. And Huygens can't save it. Huygens can't put your wave way over this edge of the surface. Huygens can't fix it. Anyway, till next time and such. Huygens isn't going to explain that double-sized maxima in the middle.